If you've ever worked around any kind of complex machinery,
Yeah.
you learn to recognize the sound of impending trouble.
Oh, absolutely. That gut feeling.
Exactly.
Yeah.
But what's interesting is that the really costly equipment failures, they rarely scream at you. They don't just, go up in a dramatic explosion.
No, instead they communicate. They send out these signals, these quiet vibrations, subtle shifts in rhythm.
And they're just beyond the bandwidth of what we can see or hear, right?
Right, that's the problem. And that subtle message, that's the source of millions, maybe billions, in unexpected costs globally. Our senses, they're just not built to register that kind of
So
data.
there's this gap, a gap between the machine's truth and our ability to actually perceive it.
And that gap forces organizations into these endless, costly cycles of guesswork, trial and error repairs, and eventually, catastrophic downtime that wasn't on anyone's schedule.
Okay, so let's unpack this. We've been diving into a really fascinating stack of industrial case studies and professional diagnostic sources,
Yeah.
all focused on solving this exact perception gap.
Translating the machine's language.
Yes. Our mission today is to understand how advanced technology turns those invisible mechanical faults into immediate, precise fixes. How it replaces that old-school guesswork with predictive certainty.
And the core context here is rotating equipment. You have to think about the infrastructure that powers everything.
Like what specifically?
Massive fans, pumps, compressors, motors, generators. These things are under intense stress, and they are communicating subtle patterns, specific harmonic frequencies.
For days.
Weeks.
Days, weeks, sometimes months before the actual physical failure. So the solution isn't just collecting data. It's making that data visible.
Making it visible, how?
By layering high-resolution vibration analysis with the visualization power of what's called motion amplification.
It sounds like the closest thing to giving a piece of steel a voice.
Yeah.
And the case study we're starting with, it seems like a classic scenario you'd see anywhere, this persistent vibration problem. Exactly. This client success story we reviewed, they were battling an issue that had almost become routine. The machine was vibrating constantly.
And the maintenance teams, they did all the standard stuff.
They ran all the standard checks. They verified alignment with their basic tools. They went around tightening bolts, checked the lubrication. And on the surface, everything looked normal.
But the vibration just kept going.
It persisted. And the risk of failure was just mounting every day.
And the problem was, as one of our sources put it, that the root cause was buried beneath layers of symptoms.
That's a perfect way to describe it. They were treating the effect, the noise, the vibration, but they couldn't get to the mechanical origin.
So let's define the tool that finally cracked this case. Let's talk about vibration analysis.
Right. So to understand the solution, you have to get what vibration analysis, or VA, actually does. It doesn't just measure how much something is shaking.
It measures how it's shaking.
Exactly, the signature. It uses sensors to capture this incredibly high-resolution mechanical data. Then it processes that data using a technique called fast Fourier transform, or FFT.
And the FFT, that's what breaks the complex vibration down into its specific frequencies, harmonics.
Precisely. So let's say your machine is turning at 60 hertz. If the vibration is spiking heavily at 120 hertz, exactly twice the rotation speed, that signature points to a completely different type of fault than if the spike were at, say, 60 hertz.
It's like fingerprinting the fault.
It is. The frequency signature tells the diagnostician what kind of problem they're looking at. Is it misalignment, imbalance, looseness, a bearing starting to go?
But even that high-resolution data, sometimes it's not enough.
Sometimes it leaves a little ambiguity, or, and this is critical, it identifies a subtle issue that the maintenance crew they just can't physically find. They know it's there, but where?
And that is where the second layer, motion amplification, or MA, comes in. I have to say, the videos of this are they're unbelievable.
It's the game changer. It's the critical differentiator. It takes those minuscule movements, the ones VA registers but are impossible to see, and it amplifies them into a visible video.
So it turns the data story into a visual story.
An undeniable visual narrative. What was an abstract frequency on a graph suddenly becomes clear, physical evidence on a screen.
So on this specific machine, the one with the persistent problem, what did they actually find? What was that aha moment?
The aha moment was discovering a subtle structural misalignment.
Subtle, okay.
And when I say subtle, I mean minuscule. Far too small for any standard visual inspection or basic alignment tool to register with any certainty. The movement was maybe a a few thousandths of an inch.
But the motion amplification made it look huge.
It amplified it into this massive clear wobble on the screen. There was no denying it.
And that tiny, unseeable wobble, that was the engine of destruction they couldn't find.
Absolutely. And this is where you have to understand the physics of failure. That subtle misalignment, even though it's invisible, it introduces this cyclic loading and stress that's way beyond the design limits.
Which creates that cascading effect the sources mentioned.
Exactly. It compromises the critical lubricant film that protects the bearings, which generates excessive heat. That accelerates metal fatigue in the seals, the shafts. If you leave it alone, that quiet little issue guarantees a premature failure.
And potentially a catastrophic one.
Potentially. And in the meantime, you're losing efficiency, burning more energy. It's just a slow-motion disaster.
The finding wasn't dramatic, but it was, as the source said, real, and it was exact. And that feels like the essential takeaway here. The biggest problems aren't always loud or obvious.
They often bypass all our human senses and all our manual checks. You have to move beyond just looking at the equipment.
You have to start using this high-fidelity data to actually read its mechanical state.
You have to measure what matters, the specific frequencies, the movement patterns, not just what's easy to check.
And that actually brings up a really interesting point about the human side of all this.
The human element, yeah.
Because we often talk about analytics replacing people, but the sources we looked at, they really emphasize this partnership between the technology and the experienced tradespeople.
It's a fantastic dynamic. I mean, experienced industrial millwrights, pipe fitters, they develop what you could call a sixth sense.
Right. They can just feel when a machine's rhythm is off or hear a tiny shift in tone.
Decades of instinct. But they're also the first to admit that modern tolerances are so tight and the issues are often so disguised that their instinct only gets them so far.
It gets them in the ballpark.
Exactly. As one source put it, the most destructive modern issues, they whisper or they disguise themselves as something else entirely. So this isn't about the millwright versus the computer.
It's a collaboration.
A profound one. The millwright's instinct gets the diagnostic team close. They know the equipment's history, they know where to start looking. But the high-res VA and the motion amplification, that gets them exact.
So instinct sets up the diagnostic, and the data guides the surgical fix. So once they had that definitive data, what was the actual fix? Was it a huge, expensive overhaul?
Not at all. And that is the beauty of precise diagnostics. Once the problem was isolated with certainty, the solution was straightforward.
What did they do?
They used precision laser alignment tools. These are essential for hitting tolerances you just can't get with manual methods. They corrected the alignment, retorqued some specific components that the VA scan flagged as loose, and then verified the whole setup against the original specs.
And the outcome? The immediate result?
It was described as an instant return to stability. The moment the correction was made, the machine's vibration levels just dropped sharply, back to its normal operating range.
Wow. So within hours, the problem that had plagued them for weeks or months was just gone.
The persistent, costly issue was eliminated, and full efficiency was restored in just a few hours.
That is just a massive return on investment. The cost of that potential downtime had to be orders of magnitude higher.
No question. But the real shift here, it's strategic. The client moved from that frustrating cycle of chasing symptoms
to actually understanding and eliminating the root cause.
They gained verifiable certainty. And by understanding why the issue kept returning, they fundamentally changed their whole maintenance approach.
So they stopped being reactive.
They stopped waiting for a failure to force a shutdown and became profoundly proactive. Using predictive diagnostics lets them schedule interventions on their own terms.
And that's what buys you confidence in your assets.
Confidence and longevity, yes.
Which leads us perfectly into the bigger picture, because this kind of specialized diagnosis, it's not just a niche troubleshooting tool, is it? It's a comprehensive shift in how we manage all industrial assets.
That's right. If it rotates, this expertise applies. The scope is just massive.
Fans, blowers, pumps.
Compressors, motors, industrial gearboxes, generators. I mean, it's literally everything that underpins industrial society.
And the services needed to maintain that reliability, they go way beyond just the diagnostics. We're talking about core precision mechanical services.
Right, like the laser alignment we just mentioned, and also static and dynamic balancing.
Okay, what is dynamic balancing?
So if you have any rotating component, say a fan or an impeller, that isn't perfectly mass distributed, it's going to vibrate. It's unavoidable. Dynamic balancing is the process of precisely adding or removing tiny amounts of weight to neutralize that rotational
To
imbalance.
make it run perfectly smooth at speed.
Perfectly smooth. And they combine that precision with full troubleshooting, consulting, and comprehensive turnkey mechanical services.
Turnkey services. So that means from start to finish.
Exactly. In-house design, supplying parts, installation, and commissioning support. It ensures that the quality and precision they demand in the diagnostics phase is actually baked into the equipment from day one.
And it all has to adhere to some really stringent quality benchmarks.
Hmm.
I see things like API specification Q1 and ISO 901 mentioned.
And that's crucial. For clients in heavy industry oil and gas, energy, LNG facilities, the stakes are incredibly high. A component failure isn't just an expense.
It's a major safety and environmental risk.
It can be. So a standard like API Spec Q1, that's a quality management system specifically for organizations that supply the petroleum and natural gas industry. It's not just a label, it's a foundational guarantee of reliability and traceability that you absolutely need in those high-pressure, mission-critical environments.
And beyond the general rotating equipment, the sources we looked at highlight a real specialization in optimizing complex systems, like air-cooled heat exchangers or ACH.
ACH optimization is a major focus because those systems are under immense mechanical stress. They're huge, they run constantly. So the specialization includes supplying high-efficiency, low-noise fan components like elliptical E-bells.
Which do what
They
exactly?
improve the airflow dynamics and reduce noise pollution at the same time, so you get better performance in a safer, quieter work environment.
I also saw a mention of the patented anti-rotation device.
That is a very specific but critical safety mechanism. On a really large fan, if a primary component fails, inertia can cause the entire fan assembly to spin backward. It's called runaway.
That sounds bad.
It can be catastrophic. It can cause severe structural damage. The DG2 is essentially a patented locking mechanism designed to prevent that exact scenario. It shows a commitment to safety engineering that goes way beyond just basic maintenance.
It's not just about being a generalist, it's about having that deep, niche engineering knowledge.
And that commitment shows up in the results. The sources repeatedly highlight documented success, including completing these complex retrofits with zero incident reports.
Zero incidents. That's impressive.
And beyond that, these precision retrofits, they often yield huge operational improvements. We're talking measured airflow performance improving by 15 to 30% in some cases.
That kind of efficiency gain plus the added reliability, it just changes the entire operational calculus for a facility. And this is all moving forward with the next generation of diagnostics, right? We're talking remote monitoring now.
Yes. They're taking the high-fidelity data collection, the VA and MA we talked about, and enabling constant digital vigilance. AI-driven systems can process sensor data 24/7 and provide real-time alerts.
So you can see the problem digitally long before it ever fails physically.
Exactly. It means rapid response teams can be dispatched for emergencies, but more importantly, it means clients can monitor the health of every single asset, no matter how remote.
So let's tie this whole deep dive together. The true value here, it seems to me, is the ability to translate the machine's quiet mechanical state into a clear, high-fidelity story.
It's the difference between operating in a state of crisis management and operating in a state of engineered predictability. It's that combination of advanced technology, the VA and the MA, paired with skilled, precise field expertise.
There's a millwright's sixth sense.
Right. And that combination makes problems that used to be impossible to locate not just solvable, but quickly and precisely managed.
If you can't accurately define the problem, you certainly can't fix it. Data, when it's leveraged like this, is fundamentally changing physical labor by making the physical world readable and predictable.
And this raises a pretty important question for you, the listener, to think about. If these subtle, almost invisible mechanical misalignments can cause massive, cascading, and costly failures in industrial equipment, then what subtle, nearly invisible organizational or procedural misalignments are causing predictable failures in our own complex business systems, in our daily workflows? And how do we build the right diagnostic tools to see them before they cause a breakdown?
Something to vibrate on as you head into your next project. We'll catch you on the next deep dive.